Okay, now that we have already agreed upon the point that we can't fit a linear regression line for a non-linear or at least a binary output, what are the other functions that we can consider? So linear function is not at all a solution. Let's consider some non-linear functions, or like the functions that are away from a straight line. Maybe a polynomial, can it be a good fit to our data? No. Gaussian function? Nope. Quadratic function, can it fit to our data? No. Can we fit exponential function? No. Sine wave? No. Double exponential doesn't fit to our data. What about logistic? Yeah, this seemed to be a good fit to our data. If you take logistic function, try to arrange the parameters in such a way that somehow we squeeze the middle portion and then expand the tails by changing the parameters, looks like this can be a good fit for our data. So that's the reason why we will not fit a linear regression line. We'll try to fit a logistic regression line. We'll try to use logistic function. So if this is our data, somehow we can fit logistic regression line, which can be a good fit to our data. At least when compared to linear, this is much better, which has longer tails and middle portion is lesser, which means it will fit most of the times for our data, whereas we can avoid so much of error rather than just fitting a straight line. So earlier we have a linear regression line whose equation was y equal to beta naught plus beta 1 x. Now for logistic regression we have a different equation. It will not be as simple as y equal to beta naught plus beta 1 x. The equation may be different. So we want a model that predicts the probabilities zeros and ones, that is like it predicts a binary output. Then it has to be S-shaped. The model has to be in S shape. So there are lots of S-shaped curves. We will use logistic model in that, which fits best for our type of data, whereas a portion of the data is for ones, a portion of the data is for zeros. We know that some portion of the people are buying, age less than something are not buying, age more than something are buying. Most of the times that's what we observe the pattern in a particular variable. As that variable grows, some values will be more value, one class will be dominating. Basically, if age is increasing, we can see a class 1 or buying class is dominating. So what is the equation, logistic equation or logistic equation? The equation, like the way we had y equal to beta naught plus beta 1 x, here the equation is y equal to e power beta naught plus beta 1 x divided by 1 plus e power beta naught plus beta 1 x. So that's it. Like earlier for a straight line it was simple equation, that is y equal to beta naught plus beta 1 x. That means a straight line. What means this S shape? What means this logistic line? The equation is y equal to beta naught plus beta 1 x divided by 1 plus beta naught plus beta 1 x. That's it. Earlier we were getting the output as direct y value or the dependent value. Here we might not, ideally we should be getting the output as 1 or 0. Definitely we will not get that. What we'll get is some kind of a probability, because direct 1 or 0, this S-shaped curve may take a lot of values. Every value it will take. So we will get any value between 0 and 1. That's why we will get something called a probability. So we will not get directly 1 or 0 class. We will get a kind of probability. We will get some values near to 1, some values near to 0, some values in between. So we have to actually classify them. So what we get is a continuous number that is between 0 and 1. We have to divide that as, okay, if we are getting 0.95, then I would say, yeah, this is class 1. If we are getting 0.001, then I'll say class 0, that is not buying or not buying. So the output will be probability, the input will be the x value, the line equation is y equal to e power beta naught plus beta 1 x divided by 1 plus e power beta naught plus beta 1 x. That's the logistic function. So instead of building a linear regression line, it's better to fit, or it's apt to fit, logistic regression line. So in logistic regression we'll try to predict the probability instead of direct values. Since y is binary, it takes only two values, 1 and 0. Instead of predicting 1 and 0, we'll predict the probability of 1 or probability of 0. And this kind of setup suits aptly for our binary categorical variables like yes or no, win or loss, fraud or non-fraud, -1 or +1, 0 or 1, true or false. We are just predicting the probability. So we will build logistic regression line instead of linear regression line. Now how do we build logistic regression line instead of linear regression line? It is simple. We don't need to write LM. Instead of LM we will write GLM, and everything else remains the same. We write GLM, stands for generalized linear models, y versus x. This remains the same, the equation type remains the same. Then data is dataset name. We are adding family equal to binomial. Why are we doing family equal to binomial? Because it is a binary output. There may be some cases where more than two outputs are there, or I mean simply you just take it for granted that we have to write family equal to binomial in logistic regression. Sometimes yes, no, not sure, or sometimes we might get more than two outputs. Simply here in our case, to fit a logistic regression line, you have to use GLM. You have to write the equation and then say family equal to binomial and the dataset name. So instead of fitting linear regression line, I'm trying to fit logistic regression line. What is the output that we are expecting? Whenever you go for prediction, you are going to get values between 0 and 1. If you are getting values that are too close to 0, that means yes, whatever is the definition, not buying or buying. If you are getting values that are too close to 1, yes, that means yeah, that value is 1. So we are getting probability as the output. So let us try to fit the generalized linear model or the logistic regression model for this data. This is the logistic regression model, and this is a summary of logistic regression model. Here also we'll get coefficient only. Here also we'll get beta naught and beta 1. But the way we write the equation is different. You remember, we have to write probability or P or y equal to e power beta naught plus beta 1x divided by 1 plus e power beta naught plus beta 1x. That's how we write the equation. It's not y equal to beta naught plus beta 1x. Now this graph doesn't make sense anymore. We'll just close this graph. Yeah. Now we will go for prediction using this model. This is a logic model. Using the logic model, age equal to 4, the person will buy or not buy. When age is 4, the predicted value is 0.002379, which is near to 0. We will consider this as 0. Product will not be, a person will not buy that product. Age 4. Age 105. Let me predict. What is the predicted value? Predicted value is 0.9999. Yes, the person will very much buy this product because it's near to 1. You understood? In fact, for the same one, we can draw the curve. Logistic regression. You see that? This is our original data, product sales, age versus bought. This is the actual data, and this is the logistic regression line, which is much more, in line with whatever the data is. Instead of this one, that was the linear regression line. It was nowhere close to our data. It was not at all representing our data. You might be wondering, we got an R square of 80% there. How will we get to know? Whatever may be the R square, at the end of the day, R square is just a mathematical value, right? Your line should be a good fit for your data. And obviously, the line that we are talking about, which is a good fit for data, is this logistic regression line. So we have to fit logistic regression line, not the linear regression line for this data. That is the use of logistic regression line, and using GLM we fit the logistic regression line inside R.